Hey guys, good afternoon. We're at lecture 8, you guys. Got 8, 9, 10, 11, 12. 5 left. You're almost through. But we have 1 homework, 2 homework, 1 more project, plus homework 2. So we're okay. Still got a few assignments to get. But project 3, it's going to be fun. Promise. We're working on making it really fun. And project homework 3 will be released next week. It's going to be basically you implementing neural networks in Keras. It should take you about 5 minutes. Yeah. Project 3 will be a lot longer. So a few components. You'll do something called transfer learning. You'll do something called T-SNE visualization or dimensionality reduction, and then visualize the results. You'll do a lot of cool things in project 3. But that'll come in a couple weeks. Before you can do all those fun homework and projects, we need to teach you about these 2 things right here: convolutional and recurrent neural networks. How many of you have heard of these things before? How many of you have heard of convolutional neural networks? How many of you have heard of recurrent neural networks? How many of you have implemented a convolutional neural network in Python? 1 person. Attaboy. 2. Cool. So after today, all of you will have raised your hand, assuming you can get your Keras version working correctly. Yeah. Very contingent on that point of getting your Keras version set up correctly. But without further ado, let's get started. So the outline for today is, first we'll give you some background about why we even need to talk about these things, why the neural networks that we talked about last week aren't good enough, why these things are so much better, and how they handle some of the problems that the standard feedforward networks pose. So we'll motivate it like that, and then we'll kind of dig deep into what a convolutional neural network is, all the different components, give you some cool applications. Then we'll do the same thing with RNNs. We'll tell you all about RNNs, talk mostly about the one that's being used mostly today, which is called the LSTM RNN. We'll tell you all about that in a sec. And tell you some more applications, some other cool stuff, and then we have a couple demos. So we have a CNN demo and an RNN demo. And we'll see those at the latter half of the class. So project 2 is due tonight, and homework 2 is due next week. And that's the only due dates so far. So project tonight, homework 2 next week. Make sure to get those in. Before we get started, are there any questions? Cool. So Olivia and I will be splitting the lecture today. So remember, if you guys remember Olivia from lecture 1.
Hi.
And I'm Jordan, if you forgot me. Yeah.
Actually, I'll just talk to you later.
Okay. Let's get it. So, like I just said, background motivation, CNNs, RNNs, question demos. Let's do it. So this is where we left off last week. Gano right there, who's walking in so gracefully right now. We talked about the feedforward neural networks last week, and they look like this. And we talked about how they're so state-of-the-art for so many things, they can do all these cool things, but there's limitations, right? And so let's talk about what some of those limitations are. And so the question I want to ask you is, why do you think these kinds of neural networks are not sufficient for every kind of task that we want to do? Yeah.
You lose data.
You lose data. How so?
I don't know if it's next to one another, it's next to this way, or like the relative position.
Sure. So with feedforward networks, you don't have a sense of translation invariance like you do with a convolutional neural network. Okay. That's one possibly proponent of CNNs. Yeah.
Each one points to 10,000. Like in the 10,000 case, each one points to 10,000 other neurons. So if you have 10,000 the layer before, then each one points to 10,000. So that's 10,000 squared, which is a pretty big number. So it doesn't scale up very.
Yeah, you can imagine that if I have a few thousand parameters in a couple layers, my number of parameters just explodes. If I have like 10,000 neurons in a couple layers, I'm already at like 100 million parameters, something crazy like that. That's a huge, huge computational complexity, both for model complexity. We're trying to fit a model with millions of parameters with a few thousand data points. We just don't have enough information to do that. So we try our best. But yeah, this is a problem, and there's ways to deal with it. Yeah, what were you going to say?
I was just going to say different structures might work better for different tasks.
Yeah, so perhaps we can design a network to work better specifically for different tasks based on the specification of the network itself. And we'll see. Yeah, we'll see that. Let's talk about why we're here, I guess. Why you guys all signed up for the data science decal. My guess is that a good majority of you are here for the 2 credits. Another majority of you are here because you've heard of data science and you want to get a good job. And I don't know why all of you are here, honestly. Why are you here? I'm just kidding. No, this is fun. This is fun. We have fun. But the point is that the stuff that we're teaching you is being widely used by so many big players in our current world, not just our little bubble of Berkeley, but the whole world. Facebook connected the whole world, and computer vision has played a large part of that. 2 Sigma is just killing the financial game, and they're launching all these deep learning teams every day. Adobe has a big research team where they just research so many cool things that they work on. Google, I don't have to speak for Google. Google is the king of deep learning. Google made TensorFlow. Deep learning is going nowhere. Spotify for music classification, maybe for some music recommendation. Deep learning is being used there. Apple, the iPhone 10 has a special chip in it made to work with neural networks. It's called like a neural chip or something like that. Bioneural, some chip like that. But it's made specifically to work well with neural networks. Genentech, they do medical imaging stuff with deep learning. Tesla, their autopilot uses deep learning. When I say deep learning, I mean neural networks, okay? And Analytic, that's a little shameless plug. That's where I'll be working, and we do medical deep learning imaging. Medical imaging with deep learning, and so that's a lot of fun. And it's going nowhere. I mean, there's the shortage for people who know this stuff is growing and growing, and the demand is increasing and increasing. But who are we to say that it's all not a hype? I've talked to many people in many professions, many professors who have lived through these kinds of hypes before, and the general consensus I've gathered from them is that yeah, it's maybe a hype, but it's warranted. It's here to stay, and the people who understand this stuff are going to change the future. If you're working in tech, if you're a teacher, if you're a 5th grade teacher, I don't know how you're going to use neural networks, but maybe. So yeah, let's talk more about that problem of having high dimension. Yeah, sorry.
Oh, just addressing the other thing you talked about, like what was hyped or not. Could you give an example of like something in the past that was like really hyped up, but then turned out to be not actually that?
Can I think of something? I want to give a good example, but I don't have one right now. But I'll get back to you.
Well, I can give a quick example.
Olivia has one.
I can give you a quick example. It's honestly something that's like not wasn't necessarily like warranted, but like for example, like just like 5 to 10 years ago, everyone was talking about mobile apps. Like creating an app and getting 1 million users was a really big deal. But now like you don't see any VC funding a company because they got 1 million users on a mobile app. So I think that's what you kind of mean by like hypes. Like there's these different trends in tech that like, oh, this is a big thing. And so like mobile was a big thing, like creating an app was a big thing. But that's no longer that big of a deal, but it was definitely warranted in its time.
That's a good example, definitely. Tech bubble, the housing bubble, hypes. These aren't going anywhere. Let's talk more about that problem of high-dimensional data, specifically with images, because I'm mainly concerned with image problems for today. So suppose I have this image that has 256 by 256 pixels. So it has a very large number of entries in this 2 by 2 matrix of pixels. So if the input is 256 by 256, the number of neurons in the input layer will be 65,536. If I have a hidden layer with 1,000 neurons, just 1,000 neurons, I'm already at 65 million parameters. If I have 2 hidden layers with 15,000 neurons each, I'm at over 1 billion parameters. And if you didn't know this already, having a lot of parameters is bad. We strive for simplistic models. There's this principle called Occams razor. Have any of you heard of Occams razor? Basically, it says to strive for simplicity for a lot of reasons. For generalization, for interpretation, for ease of training. And so when we see these millions and billions of parameters, we kind of shriek away. Turns out it's not detrimental for neural networks, but it's still something we like to avoid. mainly for computational constraints. So how do we solve that problem? We can use something called a convolution operator. And we'll talk all about what that is, but basically what these allow us to do is to vastly reduce the number of parameters in the network. So I can go from that billion parameters to maybe a few 100,000 using convolution operators. And biologically, there's experiments that were done in the late 1960s at Harvard, forgot the name of the scientist, but they found that convolutions emulate the response of individual neuron to visual stimuli. So I think Daniel talked about the cat experiment last time. It was along the lines of that. And the reason I just have that bullet point there is to motivate that there is, perhaps not is, I can't say for sure, but there perhaps may be some biological plausibility towards what we're doing here. And like was mentioned before, when we introduce these convolution operators, the reason that they reduce the number of parameters is because they're translation invariant. And translation invariant basically means that if we're looking at an image, and I guess I shouldn't say what a convolution is because I haven't showed you the picture yet, but if I have a convolution operator that's running along an image, the convolution shouldn't care where in the image the cat is located if I'm looking for a cat. So translation invariant means that it's not sensitive to where certain objects are located in the image, as long as they're there, clearly, without too much noise. So here's what it looks like, and I wish my GIF worked, but it's not working. But this is what a convolution looks like. So you can imagine this blue tile at the bottom being like my input image, the image that I'm trying to feed into this neural network. And that green tile square on top is, you can think of that as my kernel filter, my convolution filter. That this green filter slides along this blue tile and performs some kind of product, which is then fed into the next layer in the network. And Olivia will talk about all how this process works. But I just wanted to show you what a convolution is. It's basically an operation that slides across an image. Or it can also be a one-dimensional sequence. You can have 3D convolutions, 4D convolutions. There's no stop. And there's a lot of cool math behind convolutions too, but we didn't want to get into that. So another problem that we may have. So in the real world, data can often be thought of as sequential. So, I mean, a lot of people are doing machine learning on sequential data like music or text or time series, so finance, any kind of time series prediction. And the question then is, how do we feed a sequence of inputs into our neural network? So with those feedforward networks, we kind of just fed in one fixed input and then got an output, and then we moved on with our days. But what if I want to introduce more than one input? Because I have reason to believe that there's a lot of rich information captured in this sequence of data, and I want my model to capture that rich stream of data. So how does a neural network keep track of all the information it receives sequentially? And so we also have a solution. It's called recurrence. And basically the main idea behind recurrence is the introduction of loops into our neural network. So we have our neural network, but it sequentially receives data. It receives if my data is a sequence of data points, then it receives each data point in the sequence one by one, performs operations, updates its state, and then finally makes a decision. Key point is loops. I introduced this concept of recurrence and loops. So that should sound familiar to most computer scientists in the room. And then finally, I know we talked about this already, but I just wanted to say one more time about why we're about to talk for an hour and a half about all these things. Or just to show you about how these things have been used. So the top left is Facebook's machine translator. So it's translating from a language to English. I'm not sure what that language is. I don't know if someone can tell me. But so before their new model that uses neural networks, the translation was shown at the top. So it's pretty bad, right? It doesn't make too much sense. And the really cool thing is that with these new neural translation models, the translation is so much better. It's like these networks actually learn something. They're learning how to translate words. It's not just math anymore. It's like there's some learning going on, and that's what's really exciting is that second translation it's so much more plausible and realistic. Bottom left corner is just, I mean, this is happening today. We already have self-driving cars. They're just not street legal yet because of all the regulations, but it's already there. There's dozens and dozens of self-driving car companies. It's crazy. And just to keep ourselves grounded, the real reason that we've been able to do all this is because the amount of data that we have and it's just so much higher. It turns out that these deep learning models require a lot of data to make any kind of significant progress. With these, because of the models having so many parameters, it takes a lot of data, a lot of information to help learn those parameters. And so as we have more data, we can better learn the parameters in the neural network, essentially. And so the takeaway is that this massive influx of data in our world and the massive increase in computation power has that in combination with all the modern deep learning algorithms, all three of those together are what basically led us here today. And this is a cool book if you're interested, The Deep Learning Revolution by Solnowski. Cool. So now Olivia is going to talk to you in great detail about convolutional neural networks. Before that, are there any questions to this point? Yeah.
Is deep learning just regular neural networks but more nodes?
Yeah, so I guess technically I would define deep learning as neural networks with more than one hidden layer. More than one hidden layer is deep. That's how I would define deep learning. Cool. So without further ado, oh, sorry, yeah.
For a recurrent neural network, there's a loop back to the layer loop back to itself and lots of number of very
We'll see that.
okay.
Yeah. All right, here's Olivia.
Hey guys, how's it going? How's everyone's day? Great. Wow, sounds like a fantastic day. All right. So let's start talking about convolutional neural networks. So can I just get a raise of hands again one more time? Like who's like heard of CNNs? Who's heard of like actually details about the architecture? Okay, cool. So that's perfectly fine. Don't worry about it. We're gonna get into it. Just like a heads up right now, we are leaving out a lot of the math or like a lot of like some of the more intense details just because for a lot of you this is your first time seeing convolutional neural networks, and for your project and for just like going forward, it's really important to get like the high level idea of like why and how we can do this. So there is some math involved and there's some other things. So if you want more resources, like please come talk to us or like ask on Piazza. And one thing, my lecture portion has kind of followed a blog post. So if there's anything you're confused about and you don't have time to stay after to talk or ask questions, I'll be linking this blog post up online that is going to be super helpful, and it's probably the first thing I read that made everything click. So hopefully it'll click for you guys too. But yeah, so starting off with our CNN. So this is kind of what the idea of an architecture of a CNN looks like. And so we're going to be going through all these layers, but essentially it has a combination of convolutional layers, pooling layers, and then fully connected layers. And fully connected layers, going back to when you guys were doing neural nets last week, it's the same idea, but now we're bringing in two different things, convolutions and pooling. And so we're going to talk about this a lot more. So first of all, let's look at a toy example. So let's say we want to classify X's and O's. If we were trying to look at these pictures to compare what's an X and what's an O, probably like a really naive version of how we classify this is maybe comparing pixel by pixel. So let's say we had another picture of an X. We compare every pixel, and if that matches up exactly, then that would be an X. If it matches up exactly with an O, that would be an O. But as you can all probably think about, that leads to a lot of problems because not all dogs look exactly like dogs. Or for example, what he was talking about earlier, if let's say an X is positioned really all the way over in the corner, then that's not going to classify as an X. So a great example of this is a really simple X. I think how many of you guys here would probably classify this as an X if you guys just saw it? Like, yeah, exactly. So for humans, it's really easy to look at these images and say, oh, I see this pattern. There's like this diagonal going this way, and there's this diagonal going this way. But for computers, all they really see are these numbers. They see a positive and negative. So if they were comparing one by one, they don't really see the whole picture. And that's where convolutional neural networks really are important because they can actually recognize these patterns. And they actually break up these images into smaller images to help recognize these patterns. So this is what we actually call features. So one thing convolutional neural networks will do is essentially break up these images to focus on different patterns, is what we can call features. So for example, in this X, one really prominent feature is the diagonal part. We can call that maybe a feature. Or maybe it's the middle part, which is like a mini version of an X. That's another feature. Now let's think about maybe like a cat or a dog. Like what are some core features you think could be if you had we're trying to classify like a cat?
Pointy ears.
What?
Whiskers.
Yeah, whiskers, pointy ears. Can anyone give me another one? A nose. Okay, a specific kind of nose. Sure. Yeah, exactly. So that's the same idea. So So yeah, so basically what you're doing, what these convolutional neural networks are doing is picking up on smaller features and seeing how many of these features they can pick up and how many of those features actually match the bigger overall picture. So that's where the idea of features comes out from convolutional neural networks. And so as we were saying here, we have these things called filters. And filters are what they're doing is they're actually able to try and kind of figure out where are these features on image. So for example, let's say we have this diagonal, right? So we have this feature on the left that's a little mini version of diagonal. That feature is going to be scanned across the whole picture and say, hey, where can we see this feature in our bigger image? So for example, in this case, it's a diagonal, but in another case, it might be like a cat looking for ears, or it's an edge in a face, or things like that. So that's kind of the idea of filters. So an example that Jordan was actually telling me earlier is to kind of think of like when you're trying to filter features, think of it kind of as like a flashlight looking at a picture. And every time you're going over and filtering, you're adjusting the light to try and figure out what kind of feature it matches with. So again, think about the one on the side. That's going to match up really nicely with this diagonal up here and this diagonal down here. And that middle one is going to definitely not so well match up over here, but it'll match up really nicely over here. And that one will match up here and here. And essentially what it's doing is it's looking over every placement in the picture. So as you can see here, this is what we actually call convolutions. So let's actually take one of our features. So we have the diagonal feature. And we're going to actually run this through every part of our picture. And the idea is that we're going to kind of, if you're running a model, the model doesn't know where to look for this, like this feature. Like it doesn't know if the diagonal is going to be on the left side or the right side or the bottom side. So it's going to run it over every single part of the image. So we have this feature, and it's classified as like a diagonal of ones, and then the rest of it are negative ones. And so it's going to go on every part of the picture. And once it does, it's going to compare it, and it does some simple math. So it says, hey, if you have another 1, multiply by 1, and give me out a 1. If you have a negative 1, and the black's negative 1, then that also gives me a 1. But then if I have a negative 1 and a positive 1, so essentially if I have a white and a black, or a black and a white, those are going to come out negative. And so when it runs this filter over, it'll actually give me out a different output here. So for this one, it matches up perfectly. Fantastic. Okay, it's all 1s. So it's really easy to see here, this diagonal matches up. But for example, if we got, I think the next one shows us. Not really that well. Okay, so let's say instead of in that diagonal one, we were using that middle, right? So let's say we were comparing this middle one to that left diagonal. We'd see here on the, in different parts, you'd be multiplying a negative 1 and a 1. Do you guys see what I'm trying to say here? So essentially then you're not going to get a perfect 1 by 1. And so the process of doing this over your whole entire image is what a convolutional layer is doing. It's essentially looking for features, and it's mapping out the entire image and matching it to features. Yeah?
So going back to your example,
Yeah.
you use the middle x and we use it on the diagonal.
Yeah.
The diagonal would be 1s and the rest would be negative 1s.
So if we were using the middle one you said, and we were using the diagonal, yeah. So if let's say we were we multiplied the 1, and let's say the white represents 1, the black is negative 1. So we have 1 by 1, so the diagonals are all 1. But then, for example, see these the corners here? How that diagonal's white and this one's black?
Yeah.
So these would be negative 1, and those are 1. So you get a negative 1. So in your output image here, these would be negative. They'd be negative 1.
The 2 corners.
The 2 corners that didn't match.
Yep.
Does that make sense? Cool. Does anyone have any questions of the math of that? Dope. Okay. But yeah, so that's the basic idea. So once we do this and we apply this on the entire picture, we can actually look at how this feature is represented. And if you look at this, if you see the white part, so the white parts tend to kind of congregate in the diagonal. And that makes sense, right? This diagonal feature is most prominent and most correct in that diagonal. So then if you look at, for example, maybe over here, we have a negative 0.11, 11, 0.11, 0.33, negative 0.11. That's because if you look at that diagonal feature and kind of compare it to the actual image, you can see they're not similar at all, right? So does that kind of make sense? Can you guys see the similarities? And so the idea behind this is then, did you have a question?
Yeah.
What's up?
How did
Yeah, that's a great question. We're gonna get back to the end, but that's actually a really good question. Just like hold tight, but yeah. And so, what was I saying? Yeah, so essentially then when we get this out now, we kind of can see a representation of where this feature is most prominent. And so, kind of like what we were saying is now we want to figure out like one image or something we're trying to classify is not going to have just one feature. It's probably going to have a lot of features. And so the idea is we can apply all these features and get out all these different kind of stuff, like all these layers out. So you can see here, oh, this was from, can like anyone guess what like feature they used for this one? Exactly. Or what about maybe at the top? Yeah, exactly. So if you can kind of see, you can actually see like the patterns in itself in each one of these, and you can kind of guess what feature they're trying to like look for. And so now the cool part of this is pooling. So now we have like this overall like representation of the picture when we're looking for the image when we're looking for these features. But remember going back to what Jordan was talking about earlier, when we're having images that are maybe 30 by 30 or 90 by 90 pixels, like if we're doing this consistently for every single pixel, it's going to get huge. So one idea what we can do is kind of downsample and have these pooling layers, which combine and take out the most important information and kind of downsample the image to make it smaller. So essentially we're getting rid of like all the least important information. So here what we're doing is actually we're taking of like a box of 4, we're taking the maximum. So we're going to take 1, and then after we hit 0.11, 0.33, negative 0.11, 0.33. So the next one up here would be 0.33, and so on and so forth. And these are what pooling layers are doing. They're essentially downsampling the image, so you have less to work with, but you're keeping the most relevant information. And in the end, you should get something like this. So if you see, the main patterns that you got from before, they don't change. It's still there. You still see the diagonal. You still see like that middle prominent like cross kind of, and then you still see this like other diagonal. So you haven't really lost information, or you haven't really lost relevant information. Yeah.
Is there a reason why you choose a 4x4 as your
Not for this one. There's like a lot of like different interesting ways people will choose how to downsample.
They should just use a 2x2 stride.
Yeah. So we're not going to really get into like strides and like how people choose to downsample, just because like there's like a lot of different ways. But in this case, we just chose that. But yeah, like you can definitely talk to us more if you have more questions on how people choose to do that. Yeah. So like, but like another thing I want to mention is like think about a lot of pictures you see. For example, if you see someone outside of a beach, there's a lot of sand and there's a lot of blue sky. And once you've seen a little bit of blue sky, you probably know the rest of it up near it is going to be blue sky. And that's exactly what this is kind of idea is doing. It's like kind of just getting rid of excess pixels that are going to give us repetitive information or going to give us the same thing. But at the same time, if we're looking for a very specific feature, it holds on to what's really, really important. Does anyone have any questions? Cool. Okay. So we're going to move on to activation layers. And so how many of you guys remember activation layers from neural networks? Okay, so refresher, activation layers. So essentially the idea behind these activation layers for CNNs is we want to ensure that our models are robust and to prevent it from having like mathematical instability. So for like a small example like this, it doesn't really seem like that big of a deal, but when you have like layers on layers on layers on layers, a lot of times small negative numbers could like blow up into like infinity, or like you might be dividing by zeros or things like that. And so that's the idea behind these activation layers. We want to make sure like that doesn't happen because that's going to throw off our model. So a great example that's really like commonly used is ReLU. How many of you guys remember what ReLU does? Cool. Can anyone tell me what it does? Yeah.
It's less than 0%. It's less than 0%.
Perfect. Exactly. Yeah. So I think Jordan, for those you can see, is drawing ReLU over there. But that's the same idea that's happening here. So what in this activation layer is doing is it has a ReLU applied to it. And so that essentially gets rid of all those negatives. And like I said before, that kind of just helps with ensuring there isn't this mathematical instability, numbers don't blow up to infinity, things like that. So I'd say don't worry about that too much, because for what you guys are doing and for the project, it won't make a huge difference. But just keep that in mind because it's really important to know, and without things like these activation layers, your model probably won't work. So yeah. All right. So like I was saying, so these are the pooling layers. So essentially, it kind of is the same idea. I just wanted to show you what it looks like after you apply pooling. So now all those black dots are zeros. So everywhere essentially they were like a negative. Now there's a 0. And so like I said, it just kind of gets rid of all those zeros. But if you still notice, like it keeps the like prominence of like the feature. Like you can still see there the main diagonal, you can still see the middle, and then you can still see the other diagonal. So yeah, like I said, it's not going to be a huge issue if you're having a small example and you're classifying X's and O's. But when you have a super deep convolutional neural network and these like really complicated images, things like this really get important. Cool. So now let's put this. Oh yeah, what's up?
Is it possible that we're just looking for the main diagonal feature? It's possible to not have looked at top right or bottom right corners, or does the fact that it's not protected there help the model?
Wait, can you say it one more time?
Like if we're just looking for the main diagonal, the like top left part of X.
Yeah.
You don't really need to look at the top right area of the picture, here, or unless does that top right thing not being protected there help the model?
The top right thing.
Is it possible to have like the top left or part of the X? It's possible to not look in the top right or bottom left parts of the image. So you don't really, we know just intuitively it's not going to be that part of the X isn't going to be there.
So you're saying that if we know it's an X, then there's no reason to look in this part of the image.
Okay.
No, that's not how it works. No, unfortunately not, because convolutional filters drives along the whole image. It hits every single pixel in the image, and that's actually a good thing. Sure, it might be a waste if we know for certain that we're dealing with X's and that we shouldn't look in that corner. In that case, we should just cut out that square in our data and just feed in the truncated data. But yeah, it goes still along the whole image. It doesn't just pick and choose where to look.
Yeah. To follow up on your question, I guess, like, you're right, it seems kind of stupid, like, oh, we obviously can tell this is an X, but, like, think about if you were a computer, like, you don't have this intuition, you've never seen X's before, so, like, it doesn't know just because it's seen this top part that it's going to be the rest of the X, or, for example, like, maybe it looks like an X to begin with, but if you, like, once you've actually applied the filter to the rest, you can say, oh, maybe it's actually, I don't know, something else, you know? So you don't want to cut short just because you've seen part of the image, because that definitely doesn't tell you everything. Does that make sense?
Yeah.
Cool. Anyone else have questions? Awesome. Jordan, Johnson?
Yeah, like if you want a robust machine learning system, you want it to say that these two images both have X's in them. And you don't know that the X is always in the same position in every image. You want it to be robust to those kinds of things. And because we don't know the orientation of every single piece of data that we have, or new data that we will see in the future, it's better to just be robust to any translation of the data. That also helps to provide more generalization power. If it's able to see more different kinds of oriented training examples, it's better able to classify new examples that it hasn't seen before.
A good like real life follow-up example to your question. So at Facebook, for example, their computer vision program, they rely on all the public images from Instagram and Facebook to like use for like their detecting and classification purposes. And so like for them, like one of their I was there this past summer, and one of their issues was, for example, like they were trying to classify, let's say it was an apple, right? But the pictures would have like apple juice, or like it'd be like a bunch of apples or things like that. And so the idea is that you don't want to just like focus on one specific thing, but like if you have like a bunch of apples versus like one apple, you still want to be able to like classify this as like apples, you know? Like you don't want your model to like overfit essentially to only one image or like one specific example. Does that make sense? Cool, awesome, okay. Yeah, so let's put this all together now. So the whole idea we were talking about deep learning and deep neural networks is that you're gonna have a bunch of these layers stacked upon each other. And the really cool thing is these feed in really nicely to each other. So you have like a convolutional layer, and then you apply ReLU on it. So that means we get rid of all those negatives again. And then after that we apply another convolution. And then after that we apply another ReLU, then we apply pooling, so this downsamples it. And then we apply another convolution, ReLU, and then keep going until we get something maybe that looks like this. So you guys remember our diagonal examples? Now we went through this whole process, downsampled a bunch of times, convolutional layer a bunch of times, maybe this is what we get out. Now, going back to fully connected layers. So this is the part of the neural network which you guys are kind of familiar with from last week. It's essentially going to tell us, hey, what is this an X or is this an O? And so essentially what happens is we get all of these values, right? At the last layer, we get all these values. And all of them get to contribute and say, is this an X or this is an O? Now, the only thing is that, do you guys remember the whole weights that you guys had last week? Yes? Cool, so the same idea applies here. Not every single value is going to contribute the same. And I'm going to talk about this a little bit more in a sec, but some of these weights are going to be weighted really heavily, and we're going to say, we really think this value knows what it's saying. And so that will contribute more to saying this is an X. Versus some are going to say this is an O, and be like, oh, that doesn't really matter that much, so we're not going to weight it that heavily. And essentially, you get all these values at the end. They're all weighted by a certain probability. So think about some of these lines are super heavy green. Those are the ones that are weighted more. They're super black. Those are the ones that weight more. And this at the end tells us, is this an X or is this an O? And so going back to your question, how does the CNN pick these values? How does it pick these weights? How does it know all of this? Well, this is where all these ideas from last week come in. So for example, backpropagation. It's not going to know to start off with what these weights are, what the best features are, but essentially what your model is going to do is it's going to go through all these iterations of trying different things out and testing, hey, what's the best results? And you're like, well, I'm trying to figure out if this is an X and O. How's that going to work? Well, you have this training data, right? You have this set of maybe 500 or 5,000 or 500,000 images that you use to train your model. And you say, hey, try these features out, try these weights out, and then come back and get me the best weights, get me the best features, get me the best I don't think that's it, but essentially that's what it's doing. So you have all this data you're training in, you're going to test it on. And so does that kind of make sense? So going back to your question from before, you're right, your convolutional neural network doesn't know what feature to try out at first. So it kind of just starts trying out everything, and it tries to decipher, what is the best way to decide for an X and O, what's important. So for an O, it might try out a diagonal feature, but it's wait, that doesn't help me, it's not helpful at all, right? It doesn't tell me any information about an O because O's don't really have diagonals. Or maybe for a cat, you're does it have blue, I don't know, I can't think of an example for a cat, never mind. But you get my point. So essentially you're going to go through and it's going to iterate upon, and it's going to do all these things like backpropagation to actually be able to get you these values. I'm not going to get into backpropagation again because I think you guys touched on that last week. But that's the essential idea of convolutional neural networks. So applications of CNNs. this is a really, really powerful tool and are being used literally absolutely everywhere. Face recognition. So you know how you're on Facebook, it's oh, do you want to tag Jordan Prosky? And you're like, wow, that was really weird. How'd you know that? Convolutional neural networks. Scene labeling. So for example, if you're oh, let me upload a picture, and it's oh, was this taken in Berkeley, California? You're like, wow, that was kind of creepy. CNNs. Image segmentation. So for self-driving cars right now, they're trying to segment which part is the actual road versus which is the sidewalk. That's kind of a big deal. I like my cars driving on the road, not the sidewalk. So there you go. CNNs. Action recognition, human pose estimation, document analysis. So there's all these different applications of CNNs. And where CNNs are really, really succeeding is finding patterns. And that's what really distinguishes them from the classic vanilla neural network. I think natural language processing. Is CNNs even used? I guess kind of, yeah. Yeah, so you'll see CNNs and RNNs used a lot with natural language processing. Games. CNNs are really good at a lot of video games, for example, because it can take a scene and based on scenes figure out what's going on in the scene, and based on that give you an action. So that's a really good example of how CNNs and being able to pick up on patterns is really useful for games. I think, yeah, and then drug discovery, medical image analysis, in medical use right now, for another great example is X-rays. CNNs can a lot of times tell you a lot of information about these X-rays. All different types of applications. Like I said, these are a very, very powerful tool, and it's state of the art right now, being used absolutely everywhere.
The reason I put that last one on there is because I read a paper yesterday, an academic paper that was published in a journal that used convolutional neural networks to do aircraft ejection seat testing. Yeah.
Pretty random.
Everything. That's the point.
So yeah, so I think you can see there's a really huge amount of things CNNs are being used for. Yeah. So remember what I was saying about like you're gonna have labeled data, right? So when these CNNs test, you have labeled data, and you're gonna say like all these images are cats, all these images are dogs, for example. Go train them and get me the best response, get me the best accuracy, right? And so what it does is essentially it goes and looks for the best features. Because let's say they pick out a bad feature, so like I said, for example, going back to like the zeros, if there's a diagonal, that diagonal is not going to give you any good information, and it's probably going to poorly misclassify what a 0 is versus an X. And so essentially...
I just wanted to answer a little bit.
Yeah.
Sorry.
You good?
So where do we start, and how do the features get learned? Backpropagation is the algorithm we can use to compute make the gradient updates and stuff. But the real magic is gradient descent. So we start with some initial parameter estimates, like something from a uniform or a normal distribution. We just start with some random weights, and then we perform gradient descents from our training data, and we update the parameters in the direction that minimizes the loss function. And so we pick the parameters that basically give us the best accuracy using gradient descent. It's pretty simple, but really powerful, actually.
Have you guys gone over gradient descent?
Yeah, like
Okay.
every lecture. Yeah.
Cool. Okay. Yeah.
More like, not like how does it decide which features are more important, but like how does it know what a feature is? How does it know?
We also have to keep going.
Yeah. Going back, yeah. So like we're gonna keep this really quick because we have to keep going, but essentially it's the same idea. It's like you don't have to tell a network like what to look for. It essentially will scan through the whole image and pick out features. We're gonna have a demo that kind of shows you this a little bit better, and hopefully that'll give you some more intuition. But if not, like come back to us after class. There's like a bunch of really big CNN architectures. Yeah.
Yeah, so while we're talking about CNNs, it'd be really silly to not tell you about the really popular ones that have changed the world. And so this link right here is a blog post from this guy at UCLA. He has a nice summary of all like the most important 9 deep learning papers that you need to read. Many of these models are used as benchmarks for deep learning. So every time some researcher in deep learning has some cool new network or some cool new algorithm, some cool new loss function, if they can't beat these benchmark models, then no one cares about their results, because these like idolized networks are the current state of the art, the current things that are there to beat. And luckily for us, for practitioners or just anyone who wants to use this stuff, there's pre-trained versions of these really powerful networks online. And if I wanted to use one of these pre-trained networks, it's very easy to do in a neural network library. And that's called transfer learning. When I used a really large network that was trained on millions of data points and used that for my task, where I have a much smaller number of data points, maybe 1,000 data points. And when I have 1,000 data points, I can't train such a big model. I don't have enough data. So I can leverage the pre-trained model in my own personal use. And that's really one cool use, or one way that everyone's using these things. Let's look at a few though. So this was like one of the more important ones from 2012. This is when all this hype started with AlexNet. And all these models, thanks Olivia. So all these models were, I think this was for the large-scale image recognition challenge, which is on the ImageNet database. And the goal was to classify a bunch of data, and there's 1,000 different classes. So I had 1,000 different types of objects, like 1 million data points, and I wanted to classify a data point as one of the 1,000 objects. A very, very difficult task. And AlexNet, I think, almost got to human performance. So I think human performance was like 95% for top 5 classification accuracy. AlexNet almost got there. And I think VGG beat it. I think VGG beat the human accuracy. So this is from 2014. GoogleNet in 2015 just got super deep and wide and just all these crazy connections. And but it's really just a clever combination of convolutions, poolings, and softmax. It's really nothing crazy other than fancy architecture designs. But it turns out that when you construct these deep networks and throw a lot of data at them, really powerful things happen. So this is another one exception. This is one of my favorites, ResNet. So ResNet stands for residual network. And residual basically means that there are residual connections between layers in the network. So these little connections between layers that skip over layers are called residual connections. And they're really, really cool. There's a lot of cool papers on those. And they can get really, really deep. So this is an example of 3 different versions of ResNet 50. I think ResNet the ResNet models are state of the art right now. I think those are the ones with the highest classification accuracy on this ImageNet challenge. But they're all very, very close. But I think ResNet is the best architecture for CNNs to this day. Not for every single task, but in general, I would confidently say that. And what's crazy is these ResNets can get very deep. So you can compare like ResNet 50, ResNet 101, and 152, where those are just the number of layers in the network. And you can see that, yeah, like making the network deeper does make the error go down more. Deeper does do something. And that's why everyone's so obsessed with deep learning. It just sounds cool. And everyone thinks that if I can just make my models deeper and deeper, I'll win at life. And it's not so simple, but this graph does not support that point. I saw a question over there.
Epoch mean layer?
So an epoch means, there's a few ways to define epoch. Usually the way I like to think about it is a full cycle through my data set when I'm training the model. But you can artificially define an epoch as 10,000 steps. But I think of an epoch as one full cycle through my data set when I'm feeding my data set into the model. One pass is one epoch. Yeah. Yeah. So a lot of deep learning papers you'll see will present plots like this of error rates over epochs, and you'll see these jumps. And those jumps come from reducing the learning rate. So after a certain number of epochs, the training procedure is so in that the learning rate for the gradient descent updates gets lowered by a factor of like 10 or something. And that's important to basically get closer and closer to this minimum that we're looking for. We need to get our search more and more refined. We need our learning rate to be smaller. And so that's what those jumps are for. It's a good question. I didn't know what those were for a while too. But it makes sense.
What are the scatter plots?
The what?
The scatter plots. Straight lines and plots.
I think maybe one might be train and validation accuracies. I don't know. It's hard to say. There's no label on this. Cool. Yeah. No, I have my CNN demo. Don't worry.
Okay, so we're not doing this one then.
I don't even know what you're talking about, man. No one talked to me. No one talked to me about it. I'm not Olivia, man. Sorry. Questions about CNNs? Okay, RNNs. Like we said before, RNNs are networks with loops, which allow information over time to persist. And so this is one way to look at it, as this neural network that takes an input X, an output H, and A is the bulk of my network, and this recurrent part basically creates this loop. And with each new input that I feed in, there's another cycle in the loop. And you can think of unrolling this loop, so it looks like this. So there's some like forward structure in this loop. So XT is the first input, and then I update the network, and then I feed in the next part of the input, and then until I finished all the sequences for that one particular input. I finished that whole sequence for that input. By the way, Chris Kolaw has an amazing blog explaining recurrent networks and LSTMs in particular. I would refer to this link if you want more help. But let me tell you what these even are. And so recurrent networks are sequence-to-sequence models in that they can take in a sequence of data and output a sequence of data. And that is starkly different from the feedforward networks that we've seen before. And so here are some examples of sequence-to-sequence situations where an RNN would be successful. So like the vanilla neural network is on the left-hand side. That's what we've seen before. If we want to do image captioning, for example, let's say I have an image and I want to caption the image. So I want to give a sentence that describes the image. Then my input is an image and my output is a sequence of words, right? And so my input is one, but my output is many. So it's a one-to-many network. There's also many-to-one networks, which is actually what we'll do today. We talk about sentiment analysis, where we take in a sequence of text and output the classification of that block of text for whatever we're trying to classify. There's also many-to-many models where we can take in a sequence of inputs and output a sequence of outputs. That's where we can talk about machine translation, so like converting from English to Chinese or something like that. And there's also other kinds of many-to-many models. So frame-by-frame video classification is a popular problem where I have as input to my model a video, and I want to give a play-by-play, frame-by-frame description of that video, right? Or I want to classify what that person is doing in the video. If someone is swimming or someone is cooking eggs, I want to classify that that person is doing just that. And so recurrent neural networks have popularized, or have been popularized with the motivation behind many of these tasks. So one big problem with normal neural networks is this problem of long-term dependency. So you can imagine this being an issue where I have a really long sequence of inputs. And you can think of this as an issue because it may be that earlier inputs in the sequence may have some relevant information with respect to later inputs in the sequence, but they're so far apart that the computation may have jumbled things up. And so this long-term dependence is an issue because I want to make sure that my model keeps track of everything that I've gotten it, even over a long period of time. I don't want it to forget anything. Maybe I do. Maybe I do want it to forget things and to remember other things. But I want to keep track of this dependence over time. And so here's an example. I grew up in France, ... Maybe there's some like other sentences there. And then the last part is I speak fluent French. And clearly there's some long-term dependence between the word France and French. And that's something that we want a neural network, or our recurrent neural network, to capture. And this is a problem, and a normal recurrent neural network can't do that. But we have solutions, and they're called LSTMs, and that stands for Long Short-Term Memory Network. And it was introduced by Hawkrider and Schmidt-Huber in '97. And this type of recurrent network is capable of learning long-term dependencies. And that's huge, right? That's absolutely huge. That's something that neural networks haven't been able to do before. But for LSTMs, the way these work is rather than a single neural network layer, there are 4 neural networks inside the same layer which interact in a special way. And we'll see how that happens. See how we're doing on time. Okay, gotta go kind of quick. Cool, so this is inside of an LSTM cell. So maybe the left-hand side is the previous loop, the right-hand side is the future loop, and the middle thing is our current loop. And inside this neural network, there's 4 neural network layers. A sigmoid, a tangent, a sigmoid. There's some pointwise operations like additions and multiplications. There's some concatenations where I combine the outputs of 2 different layers. And they're combined in a special way, and then their output, and then what's output from this middle cell is a hidden state and a future cell state. So there's 2 things that are outputted by each one of these LSTM cells, a hidden state and the following cell state. Okay, and we'll go further into detail about what each of these layers does. But at a high level, what they try and do is to forget and remember things that they should forget and they should remember. The core idea is this thing across the top of the cell state. This belt across the top, which we can think of as the cell state. And the cell state kind of keeps track of the information over time. The cell state is like this thing that goes across time, across our network, and keeps track of everything. And within a single loop of the LSTM can add or remove information from the cell state. So as I take a new input into my model, I can update the cell state accordingly. I should maybe forget certain things and remember new things from this new input. And as I said before, these gates that we see below the cell state are just made up of neural network layers and pointwise multiplication operations. Nothing too complicated. But these are the 4 kind of gates in an LSTM. There's an input gate, a forget gate, an update cell state gate, and an output new hidden state and new cell state. Those are the steps. So the first step is to take in the input, and once I take in the input, the first neural network layer decides how much of that new input to feed into the cell state. If it's an important input, we should feed a lot. If it's not an important input, we should not feed that much. After that, we hit the forget gate, and the forget gate is telling us that we should forget a certain percentage or a certain proportion of our previous cell state. So maybe things that happened way in the past or just not relevant anymore, we can just forget. And so the forget gate scales the input between 0 and 1 because it's a sigmoid. The forget gate is a sigmoid neural network layer, and sigmoid scale values between 0 and 1. And so you can think of as if the neural network scales the input to 0, that means we want to forget we want to forget all of it. If the forget gate is 0, that means we forget all of it. If the forget gate is 1, that means we remember all of it. And so that's how you can think of the forget gate, as determining how much of our previous input we're maintaining. There's an update cell state with just more pointwise multiplications from the outputs of the previous gates. And then there's another gate which outputs the new hidden state and new cell state. It's pretty complicated. There's no reason to spend time trying to bang your head against the wall trying to figure this all out now. I just wanted to tell you what each of these things were inside of an LSTM, give you the intuition behind forgetting and remembering things in order to capture long-term dependencies. And the rest you can read up on your own. It's complicating stuff, yeah.
Is there a limit to how much the hidden state can remember?
Is there a limit to how much the hidden state can remember? I would say yes. I don't know how to put a mathematical bound on it though. But maybe there's a way. I don't have a good answer though now. So as we've, yeah, sorry.
Is the cell state actually used as an output in anything? It seems like the cell state is being updated, but I don't see where it's used.
So it's combined at this little spot right here. It's used to output the new hidden state. And the hidden state is being used for the following loop in the recurrence layer, yeah.
Do you update the cell and bits only in your training model, or are they still updating your predicting?
Only, so the updating of parameters only happens during the training process. Yeah, when I'm testing my model on some validation or test data, there's no updating. I'm just feed forwarding my data through the network end to end. And there's some really cool applications. So some things that I've worked on are sentiment analysis, time series prediction. Daniel's worked on music composition, but he left. So there's some biologists in the room. There's some protein homology detection applications. There's so many things you can use these sequential models for. And they're not going anywhere. There's, I think just about every day there's a new kind of recurrent cell proposed. So the LSTM, there's lots of different kinds of recurrent cells. The LSTM is kind of the most popular one and the one I chose to talk about. But there's things called GRUs and EUCNNs. They get really crazy. And just about every day there's like a new one coming out. And all they're trying to do is beat the one before it. But at the end of the day, what they're doing is these really cool things. And yeah, they're changing the world. So we talked about a lot today, but we didn't have time to talk about everything. So some things that we didn't mention are about how to actually train these large networks with lots of data on GPUs. So the networks that we'll train in the homework and in the demo are kind of small networks on small data sets, and they're doable on our personal machines. But you can imagine that when I'm dealing with hundreds of thousands of images that are very high dimensional, and my networks have a billion parameters, that my machine would rather just turn off than do any kind of computation. It'll just freeze and ignore you for probably a couple days. And so it's really important to have, or to at least be aware of, how to train big networks on big data. And you can use GPUs and TPUs, which stand for Tensor Processing Units, but those aren't publicly available yet. So there's also networks which combine convolutions and recurrent layers in them. So that's something that we didn't talk about today. But some things that use those kinds of models are like video action recognition, where I have a sequence of inputs and a sequence of output. And so I can use a CNN to reduce the dimension of my input image of the input frame. Once I have the reduced representation of that frame, I can feed in the sequence of representations for that frame into the recurrent network, and the recurrent network can classify the scene of that original image. So that's one example of how you can combine a recurrent and a convolutional neural network. So I talked a little about transfer learning, but not enough. Transfer learning is super important and one of the most applicable things. And for that reason, I'm making you a nice big component of it, making you a nice big piece of it for Project 3. So stay tuned for that. That'll be released in a couple weeks. Another problem with neural networks that we haven't talked about is how to interpret these things, man. Like, these things are so crazy with millions of parameters, and we don't know what we're doing. We're just seeing like accuracy go up, and we're just happy, smiling. But we don't know like how robust these networks are. We don't know what's really going on under the hood. And so there's a big, big effort to figure out exactly those questions. Figure out what the filters of learning, figure out what kind of things maximize certain things in the network, to actually figure out what's being learned and how it's being learned. And so there's many other kinds of neural networks that we just don't have time to talk about in this class. There's autoencoders, neural Turing machines, generative adversarial networks, there's so many really cool ones. And something that we didn't talk about is the future of all of this. Where is deep learning going? Where are we going to see convolutional and recurrent networks in 5 years from now? Those are the things that are really interesting, but we got to hit the demo, you guys. We got to do this stuff ourselves. We can't just keep talking about it. So are there any questions before we start the demos? Yeah, I saw you first.
So when you say like it's kind of a black box, if you're not really sure what it's filtering, is it because you're not sure what the patterns it's picking up, or like what did you mean by that?
Yeah, so there's a lot of ways to interpret that black box. So the black box, I like to think of it as we have this very, very complex like model with lots of connections and so many millions of parameters. And how do I interpret those parameter values? That's a really big question of concern for us as practitioners.
Have you heard about Google's AutoML?
I've heard of it, yeah.
So, like, what do you think about that, like, in terms of sort of going more deeply in terms of education into machine learning or artificial intelligence?
I'm not too confident with their AutoML program. Let's talk more about it after though. I'm not too scared though, if that makes you feel any better. You shouldn't be scared either. Some questions? So I have 2 demos. We have this fashion MNIST demo for CNNs and this sentiment classification for RNNs. So how many of you have heard of the MNIST dataset? The handwritten digits 0 through 9. And so it's kind of one of the more canonical data sets that we use for machine learning. It's just a set of a few thousand images, 28 by 28 black and white images that are labeled 0 through 9, and basically a bunch of postdocs in Canada labeled images and made us a nice data set. I think it's a nice data set, but it's kind of boring. And so I wanted to use a cooler data set, and it's called Fashion MNIST. And what it is it's a collection of images, but rather than having the images being labeled 0 through 9, I now have 10 different types of clothing. So I have boots and shoes and jackets and sweaters, and I want to create a neural network that can classify the type of clothing that I feed it into. Okay. Let's do attendance real quick. Oh, so close. You guys almost had the demo. Quinn, do you know the attendance form? So tinyurl.com/ I think it's
Neural networks on steroids.
neural networks on steroids. Can you open the responses? All right, I'll give you like 2 or 3 minutes to work on that, and then we'll start the demos. January.
Oh man. Never heard of it.
Is anyone still working on the attendance form? I'll give you one more minute. Okay. Let's get back to it. Okay. So I'm going to show you how to implement convolutional neural networks in Keras, with the task being to create a fashion MNIST classifier. And so we'll see what all that looks like. These are just all the imports that I'll need. So MNIST reader is some function that I've borrowed from someone. So make sure to import that to read the fashion MNIST data. NumPy, matplotlib stuff. So all this Keras stuff are basically all the layers that Olivia described implemented in Keras. So very easy to use. It's not hard to do what Olivia said, even though it may sound like it. We'll see that. So I need to import a dense layer, the fully connected layer. I need to import the activation layer, the flattening part, the dropout, the convolutional layer. I need to import the max pooling. And then I want to import a two-categorical utility, which will allow me to categorize my labels. We'll see how we use that in a sec. Okay. So first step that I want to do is to import the data. And so this MNIST reader is already a nice function that splits up my data into X and Y sets like this. And so I can import the data like this follows. Okay. Cool. And so the data comes flattened out. So the images, rather than being 28 by 28 images, they come as one big long vector of 784. So each image comes as a 784 dimensional vector. And because I wanted to use convolutional neural networks, I should change that into a 2D shape. And so the way I can do that is using NumPy's reshape function. And I give it the new shapes. I want to have 60,000 training images, 10,000 test images, each of size 28 by 28. Okay, so now let's visualize these images. Let's see what these fashion MNIST classes are. Cool. So a boot, a shirt, a dress, a long sleeve shirt, some shoes, some stilettos, jeans, jacket, dress or coat, and a purse. And these are just 10 examples. We have like 60,000 of these images. There's probably like 6,000 of each kind of clothing article. And I'm going to get my network of all these data points, and at the end of the day, it should be able to tell me what a given article of clothing is. Okay, so standard practice is to separate into a training and validation set. So the reason to do that is to make sure that I don't overfit to the data set that I have. And basically, I'll be training my model on the training data and using the validation data to validate my model. And I can do hyperparameter tuning on the validation data, as you've seen in your homework. Something subtle here that I've done is, because this data set's a little bit large, and I don't want to kill all our computers, I just took the first 16,000 as my training images, and the next 4,000 as my validation images. So normally there's 60,000 train images and 10,000 test images. I've taken 16,000 train images and 4,000 test images. or validation images. Only reason I did that is to make computation easier. Okay. So there we go. There's our data. And we're essentially done. We have our training data ready to go in 2D format. It's 28 by 28. It's not pre-processed yet. So I didn't talk about centering or scaling the data yet. I actually won't talk about that today, but something that I should talk about is data pre-processing. I forgot to put that in here, but it's really important. So I'm going to make a note here. Do data pre-processing. It won't be detrimental, but data pre-processing involves things like scaling the features in our data. So like mean centering each feature and perhaps dividing by like the L2 norm or something like that to get the values on the same scale. That may increase performance by like 1% or 2, but it's not anything crazy. And sometimes you don't want to scale or pre-process. For certain applications, you don't want to do that. So it's not always the right thing to do. But without further ado, let's build our first neural network. So I'm going to choose to build a neural network with 3 chunks. So it's going to have 3 pairs of convolution pooling. So it's going to have convolution pooling, convolution pooling, convolution pooling, fully connected, classification done. So that's what it's going to look like. And so I needed to define some parameters to actually build that network. So num filters 1 is the number of convolution filters I'll have in my first convolution layer. Num filters 2 is the number of convolution filters in the second convolution layer, and same thing with 3. You notice that the number of filters increases as I get deeper into the network. One reason I can get away with that is because as I get deeper into the network, my input image shrinks and shrinks, and so I have less parameters, and so I can afford to have more filters. And the idea is that different filters pick up on different features, and the more filters I have, the better or worse, depending on how many I have. Yeah.
Yeah, we have to make a consideration that like the first input image is like the most detailed, so you should have more filters.
No, you should shuffle your data every single time. You should never have a case where one training example is more important than all the other ones. That's bad data.
Oh, maybe like if you have like a bigger image, like 100 by 100 or something like that, then that's gonna have the most information about like what this
As compared to a 28 by 28?
compared to like once you run through the filter once, then like you already kind of make your assumption.
Not necessarily. Yeah, it doesn't exactly work that way, unfortunately. Or fortunately, actually. Cool. So some other things I had to define. One sec. So I had to define the number of dense neurons in my fully connected layer. I have to define the size of my convolution filter. So filter size 3 means that my convolution operator, the thing that slides across my image, will have size 3 by 3. And you may be wondering why it's so small. It turns out that it's been shown that having more small filters is better than having few bigger filters. So 3 by 3 filters often work very well. The pool size is 2. So that means I'll be taking max pooling over 2 by 2 regions in my image. So for every 2 by 2 block, I'm going to take the max pixel and have that go into the next layer. And then I'm going to have some dropout. So I believe Daniel talked about dropout last time. It's a way to reduce overfitting in neural networks. You had a question.
Can you explain again why the filters increase as you go?
Because I wanted them to. But I can make them decrease too. The reason I wanted them to increase is because I have reason to believe that more filters will provide me with more features, which will provide me with more complexity in my model. The reason I can get away with having more filters deeper in the network is because you've seen that all the pooling and convolutions reduce the size of my image. See ya. Sorry. Reduce the size of my image. And so by the time I'm pretty deep in the network, there's not much of this image left, and so there's the number of parameters is not so big as it was earlier in the network. It doesn't require as many parameters to have another filter later in the network as it does earlier in the network because the input size is much smaller. Okay. So the very first thing I have to do in Keras to initialize a neural network is to create the sequential object. So the sequential object, you can think of it as just like a Keras model object. That's all. Empty model. But you have to initialize it first, otherwise you can't add any layers to it. Okay. So I said I'm going to have 3 chunks. Let's go through each chunk. So the first chunk, the first thing I'm going to have is a 2D convolution layer with 8 filters, 3x3 filter size, ReLU activation. And for the first layer, I'll have to specify the input shape. For subsequent layers, I don't have to do that. But for the very first layer, I have to specify the input shape, which is 28 by 28 by 1 here. This padding equals same means that I want to include 0 padding in my model training process. 0 padding is a way to ensure that my output has the same dimensions as my input. I don't want to get into that, but there are lots of utilities of using 0 padding. Really all it does is it adds zeros around your image. So, one sec, let me draw you a nice little picture. So if I have an image with 4 pixels, 3, 72, 61, and 4, 0 padding would just add like a pad of zeros around this. So I would have like basically just a lot of zeros out here. And that's 0 padding. Okay, so after the first convolution, I'm going to do a max pooling, and I'm going to take the max out of 2x2 strides. So that's this pool size, 2x2. I'll do the same thing for the second chunk. Same exact syntax, except I don't specify the input shape, and I have a new number of filters. And then I have another max pool. Same thing for the third chunk, another conv, another max pool. After the third chunk, I need to flatten my square representations into a flattened representation so that I can feed it into my fully connected layer for classification. And so this model.addFlatten things turns those 2D representations back into the 1D vector that I want. And then I add a fully connected layer. So dense is a fully connected layer. Num_dense is the number of neurons I want. And I want a ReLU activation. And then I add dropout as a way to reduce overfitting. And then my final layer is my output layer. And it's another dense layer. And it's going to have 10 neurons because there are 10 classes here. So the number of neurons in the output layer is equal to the number of classes that you have. So the ImageNet thing with 1,000 classes had 1,000 neurons in the output layer. Here I'll have 10. And then because I want to do classification, I need to use a softmax activation at this last output layer. This softmax is very important. Without this softmax, you won't have any classification being done. Softmax turns your the output of your feedforward network into probabilities, and then your classification is the class that has the highest probability of being true. Okay, so I defined it. Let's look at it. So model.summary just prints out like what I just built. So it's a nice way to visualize what we just did. So I started off with this convolution 2D. And so the dimensions of that input layer are 28 by 28 by 8. 8 is the number of filters. So the number of filters will be a dimension in like our layer dimensions, quote unquote. And you can see that the actual spatial dimensions decrease as I get deeper in the network. So the 28 by 28 is the spatial dimensions. And after the first max pool, it's down to 14, 14, and then 7, 7, 3, 3. So this image is shrinking from 28 by 28 all the way down to 3 by 3. And we're still able to maintain significant information in that 3 by 3 representation, as we'll see. Okay. So in total, we have 82,000 parameters. Not too bad. So as we saw last time, we have to actually compile and train these models. So once I've built this model, I need to compile it. Compiling it means giving it an optimizer, which tells it how to do the learning. So an optimizer is like a version of stochastic gradient descent, which is the way we update the parameters. Atom is one optimizer that just works best in practice. It's just a very clever version of stochastic gradient descent. I need to compile it with the loss function. Here I'm using the categorical cross entropy loss. because I'm doing classification for more than 2 classes. If I had 2 classes, I would use the binary cross-entropy loss, but with more than 2 classes, I'm going to use the categorical cross-entropy loss. And then metrics equals square brackets accuracy just tells me that I want to keep track of accuracy during the training process. I want to keep track of training and validation accuracies and store those values somewhere. Okay, and then I'm going to create a variable history that keeps track of all the training history. Basically, keep track of the loss and the accuracies over epochs. Okay, so I've compiled the model. I need to fit it. To fit it, I need to give it training data, a batch size which specifies how many images I'm giving the model at a time, and then I need to give it some validation data on which after every epoch it can evaluate itself on the validation data and see how well it's performing on data that it hasn't seen to train on. And then I give it 10 epochs. So I want to go through 10 cycles of the data. And so let's do it. Oops, I need to... Cool. And so one thing I really like about Keras is like the status update bar that runs across the bottom of the screen. It's like really exhilarating, right? It just gets closer and closer to the end, and then your accuracy goes up. It's really exciting. And so things to look for, if our model is doing what we want it to, if it's actually learning, then the accuracy should go up and the loss should go down. And really what we care about is the validation accuracy. The validation accuracy tells us how well our model does on data that it hasn't seen before, which is kind of our best measure of how good a model is. How well is it able to generalize to the real world? So it's training. It's a little slow. My computer froze, but it happens. It'll unfreeze in a second. The haikus from last week, so funny. I spent like half an hour the other day just laughing at them. You guys are hilarious. Yeah, after the demos, I'll read some of the haikus. No! Wait. Oh, it worked. I waited and it worked. That never happens. But yeah, it worked, and my validation accuracy kept going up, and I imagine that if I kept training it for more epochs, it would go up even more. But for demonstration purposes, I think you guys get the point. We trained a neural network, it learned how to classify articles of clothing, and it got smarter over time. And now the world is yours. You know how to build neural networks, you see how it's not too complicating, and now the world is yours to play with. The types of networks that you use, the connections that you use, the number of filters, the number of layers, the types of layers. There's infinite number of combinations of neural networks you can build, and that's where the fun begins. Okay, so let's examine the training process. Let's visualize how the accuracies and the loss changed over time as I trained it. Okay, so here's the training and validation accuracies versus epochs. So as more epochs went on, both accuracies went up. But as the number of epochs increases, there's a diminishing return to the increase on the training accuracy. For each increase in epoch, training accuracy increases but by less and less each epoch. Same thing for loss, but we see loss decreasing. So like I said, we should see accuracy increasing and loss decreasing, which is what we see. So we can say that our neural network has learned something. And yeah, I just wanted to have a little quick demo with this to show you about like the basics about how to use this stuff. Homework 3 will be you guys just doing this in Keras for both CNNs and RNNs. It's not scary. Like James made really good skeleton code. It should take you all of 5 minutes if you paid attention at all. But it's really good to know how to use Keras. Keras is, I think, one of the easiest and best neural network platforms or neural network libraries. Keras is a wrapper on top of TensorFlow. So I hope you've heard of TensorFlow. Yeah.
So you just show how to classify one thing as an image.
What? Sorry?
You just show how to classify one single item in the image, right? How do you go about like training a model that will classify multiple
Oh, so like if I want to give it an image and I want the network to say, oh, there's a shirt and socks. Much harder problem. It's a lot harder to do those kinds of things. It involves segmentation and a lot fancier attention network type stuff. Yeah, but it's an active area of research. It's not a trivial problem at all, but definitely something, good question and worth investigating. Other questions before we move on to RNNs? Let's do it. Okay. So now what we're going to do is sequence classification with LSTM, RNNs, and Keras. And most of it was from this guy's blog. This guy has a nice blog with Keras, so check that out. What we're going to do here is we have data movie reviews. So I have a bunch of IMDb movie reviews, like 50,000 of them. And I want a neural network to give it a review, tell me whether that review had positive or negative sentiment in it, whether that review was talking positively or negatively. That's what I want my neural network to do. And you can imagine why I need a recurrent neural network, because my input is sequential. My input is a review. A review is a block of text, and so there's a sequence of words, and so I should probably think about using a recurrent network. Okay, so let's start with the imports. Same Keras imports. Keras actually has the IMDb data set built in. And for LSTMs, we need to import the LSTM layer. And another thing for LSTMs that we'll need is the embedding layer, which allows us to go from these words that we see, like these raw words that we get in a review, to some vector embedding of that review, which can be fed into the recurrent network sequentially. So this model does take a lot longer to train, but I'll see if we can finish it before class ends. Okay, so I'm going to load the data set from Keras using the IMDb functionality, and I'm only going to look at the top 5,000 words. And so the way this data is going to be generated is for each review, so I have, let's say, 50,000 reviews, my data point is not just the raw text. What this is doing is it's looking at all the reviews and it's counting the 5,000 most popular words. And for those 5,000 words, it's going through each and every one of the reviews and counting the number of each of each of those 5,000 words. Okay? Does that make sense? It's counting the number of words in each review, the 5,000 most popular words. And so the data set itself kind of looks like this. So maybe I have a bunch of pieces of text, and A is the most common word, and that text X1 has A 200 times, it has dog 37 times, and love 1 time. This one has dog 400 times, and love 700 times, etc. So that's what this data looks like. It's word counts. Okay, so some pre-processing that's nice to do is to truncate and pad the input sequences. So now I want to get it down to a much shorter length. Oops. So the truncation is going to basically cut off the reviews that are too long and make sure that all reviews are the same length. Actually, yeah, so it's word counts. Okay. Okay, so yeah, our data is pre-processed. We've pre-processed our text data. We've counted the number of words, of most important words. We've truncated it to keep it all at a reasonable length. We've padded the input sequences to make sure that the short reviews are all the same length. So it's important to have the data set all have the same length. So that's why we do padding to make the shorter reviews longer, and we do truncation on the longer reviews to make them shorter. And we made it so that the reviews have a length of 500. So as you can see here, creating the model is quite simple. the embedding vector length is 32, which means that I want to embed my count representation of my data into some 32-dimensional representation. So I'm going from the 5,000 most common words to 32 features that represent those 5,000 original features. It's an embedding. It transforms those 5,000 into the 32 most encapsulating features. So again, the first step is to initialize the model with the sequential function. And then for an LSTM, the first thing we should give it is this embedding layer. We have to embed the words. So we add the embedding layer, we give it the top words, the length of the embedding vector, and the input length, which is the max review length. We add dropout because we like to reduce overfitting. And then we add an LSTM cell with, or we add an LSTM layer with 100 LSTM cells. So someone asked earlier about how we control the number of loops. Yeah, I have 100 LSTM cells here. Add more dropout because overfitting sucks. Add a dense layer with a sigmoid because I want to do classification. So remember I said last time that the number of neurons in the output layer should equal the number of classes? It's not the case when the number of classes is 2. When the number of classes is 2, the number of neurons in the output layer can either be 1 or 2. If it's 1, I have to use a sigmoid activation function. If it's 2, I should use softmax. But they're the same, they'll give the same exact answers. So I can have an output layer with 1 neuron and use a sigmoid, or 2 neurons and use a softmax. What the sigmoid does is it scales the value between 0 and 1, and if it's above 0.5, it goes to class 1. If it's below 0.5, it goes to class 0. The softmax actually assigns probabilities to each class, and then your classification is the class with the higher probability. Okay, so we added our output layer. Again, we need to compile it. Here, because we're doing binary classification, the reviews can be positive or negative. Using the binary cross-entropy loss, the atom optimizer, and accuracy for my metrics. Okay, so here's what it looks like. 213,000 parameters, and I can fit it and evaluate it. I don't want to do that just yet because I'd rather fit this network. So I can fit it and it should get an accuracy about 90%. So this LSTM network is able to classify the sentiment of a movie review with 90% accuracy. And you can make it fancier and get 95% or 98%, but it takes more time and more time, which we don't have. The last thing I wanted to show you is combining convolutional and recurrent layers. So taking this same network that I built above, I'm going to add a convolution layer to it. So after the embedding layer, I'm going to add a 1D convolution to that embedding. So I'm going to convolve over that one-dimensional vector, or it's 32-dimensional, but it's flat. I'm going to do a 1D convolution, and that's going to add more nonlinearity and also provide some spatial information. And then I'll add another max pooling, but this time I'm doing max pooling 1D, not 2D, because my vector embedding is a one-dimensional vector. That's why I do one-dimensional convolution, and that's why I do one-dimensional pooling. For images, I do two-dimensional convolutions and two-dimensional poolings. This is not an image. I add my LSTM layer with 100 LSTM cells, a dense layer for the classification, compile it with the entropy loss and atom optimizer and accuracy metrics, and summarize it. Okay, so it's the same thing, but we have a convolution layer before the LSTM part. So let's fit it. And so the results of this model are faster than when I don't include the convolution layer. And I don't want to say why exactly yet. I want you to think about it. And we can talk about why adding the convolution might make this faster. It's actually a lot faster. It's about twice as fast if I add this convolution layer. And in fact, the results are slightly better. So let's fit it. So this time I'm training it for 3 epochs. And there's 25,000 training samples. And it's going to take a while. About maybe like 4 minutes per epoch. So it should be done by the time class is over. And it's having a hard time, so the accuracy isn't really going up now. And that's indicative of us needing more data to actually do some learning. And so you can see that the accuracy is starting to slowly go up, and it'll go up and up and up and up as the training process goes on. And at the end of the day, what we have is this really fancy architecture that has a convolution layer and a recurrent layer in it that can take as input a movie review. So some person on the internet wrote a review for a movie, and this model could take that review and output whether that review was talking positively or negatively about the movie. And sentiment analysis is one very common practice in natural language processing using LSTMs. There are a lot of other things which we haven't talked about that use LSTMs that either are just too complicating, we don't have enough time, or the data that we need to use is too complex for a laptop setting. But I really hope that we gave you the general gist of these modern state-of-the-art neural networks, and yeah, I really hope you just take that away. Know that these exist, know how to implement them in Keras, spend some time learning Keras, do it for your own sake. It's quite easy and really, really useful. And again, you'll have more practice with all of this for the third homework and project. Are there any questions? Yeah.
So what would you Arden?
So I guess there's no exact answer, but like the answer I would give is when I'm dealing with images, use CNN. When I'm dealing with non-images, when I'm dealing with data that's sequential, that's not an image, use an RNN. So any kind of text or finance data or something like that. Yeah.
I hear a lot about like when you sequential every time is a different number of cycles. But we just kind of talked about when you have a bunch of them at the center and you train on that. So is there a way to put them more if you just say one more data point, not having to retrain using all of them?
So you're saying like I can train a network on a small data set and then add more data to it? And just train it on the new data?
Well, it seems like from what we talked about, what we've gone over is training on like one data set rather than having already trained more data.
Yeah.
Training on more data.
Yes. Oh, so you're asking when I would use a pre-trained network to use? When would I want to, rather than building my own network, when would I want to go download VDG16 with the ImageNet weights and use that for my classification? And yes, the answer is yes, and there are a lot of times you'd want to do that. That's a long conversation that we could talk about after class though. Yeah, there's a lot of things like you can do there. Any other questions? Yeah. There's one input, but there's 4 gates. There's like an input gate, a forget gate. Oh, for the LSTM part? It's just the number of LSTM cells. No, so here my data is a sequence, and I'm feeding in the sequence one at a time. And the sequence is going through these LSTM cells, sequence by sequence. Look at Chris Kola's blog. I think Chris Kola can explain it much better than I can. So I linked Chris Kola's blog in the slides. Best resources for LSTM. I'll admit that he does a much better job of explaining it than I can. It's non-trivial. It takes a lot of time to stare at and really figure out what's going on. And even if you think you know what's going on, it's still a lot of like mumbo jumbo. It's a lot of voodoo stuff that kind of we put things together because we think it works. They work on some tasks, so we call it working. And with some sense, that's okay. It's not the worst thing to do, but it's also dangerous. Yeah. So the question was, how do I determine how many layers I have, and how do I determine the size of the layers? And yeah, there are some heuristics. There's no concrete strategy as to how to go about picking an architecture, but there's lots of heuristics. For example, like If you're overfitting, you want to reduce the number of parameters. If you're underfitting, you want to increase the number of parameters. If you think that you have enough data that you can get away with having deeper and deeper layers that extract richer and richer features, you can try that. It's all empirical. It's all trial and error is what it is. And hyperparameter tuning on validation sets. It's as much art as it is science, is what it is. Cool. So this thing is still training. Cool, it's at 90%. Cool, we did something. That's all I had for today. Don't forget the project's due tonight, homework's due next week. Next week we'll talk about AWS and big data. So these things about how to compute these, how to do these large computations with large deep neural networks with large amounts of data. We'll talk about that next week with using AWS, Amazon Web Services, and we'll also talk about a very, very easy but very, very powerful algorithm called nearest neighbors. But yeah, cheers. Yeah.